Okay, so I'm going to start this problem. This is the fourth problem from the lecture notes for chapter 7. I'm going to go ahead and apologize ahead of time. I have COVID at the moment, so I might cough a little bit, I might sniff my nose or whatever. Also, the back door is open, so Rocky might bark, and of course he shares the yard with a few other dogs, but we'll do the best we can. All right. So anyway, one of the things that I'm going to do with this particular problem is, off to the left, I'm going to put the times that you will see all of these particular problems, A through F when they are worked. I love this problem. This is going to be maybe the first time, maybe the only time all year we will do something in 3D. So that will be a little bit interesting. So first I want to kind of draw a picture of what's going on. I'm going to use this sheet of paper to kind of, be our pictures and our free body diagrams. Okay, so the first part, let's go ahead and get our givens. Okay, so we got, the mass is 500 kilograms. We know that the curve has a radius of 100 meters. And that the velocity of the car is, now remember this velocity is tangential. So I'm not going to actually put the little t down there, but remember that this velocity is tangential, so it is the rate that it is going around this circle. Okay, so let's go ahead and draw a picture of what that looks like. And so we're just going to draw an arch, and and it's not really important where we put the car, so I'm just going to put it where the car kind of suits me. And we're going to note that the outward direction, as always, is the radial direction, and the tangential direction is tangent to that line, and technically it should be counterclockwise. Okay, cool. Now I want to think about this particular drawing. Now that I've done my drawing, I'm going to go ahead and make it a free body diagram. And what I'm going to do that, I'm going to erase the curve itself, or just going to make it kind of like, dashed line or something. I need to make sure that, that I know that it is not real, right? Because the things that we want to draw on a free body diagram, if you remember, we want three things on a free body diagram. We want the system, which in this case is the car. We want the forces on that car, which I guess we have to get to. So this particular free body diagram, I want to note, is the overhead view. And so in that direction, let's think about the forces. So that means we're looking at the things that make it go left, right. We're not worried about up, down in this particular drawing, right? So let's see. So the only force that's making it go, the force that's making it turn is going inwards, and that is the force of friction. So that's the force between the tires of the car and the road itself. Okay, let's see. I want to note that the Z direction, the Z is straight up and it is out of the page. And this is according to a right-hand rule. So if you wanted to do an official right-hand rule, what you would do is R. So if you take your right hand, and the fingers of your right hand will be the R direction, and the palm of your right hand will be the T. Okay, and so if you do that in space in front of you, you'll see that the Z is going straight up, okay? And that will kind of give you an idea for which way Z is. So, I mean, Z only has two possibilities, straight up or straight down, but in this case, it's straight out of the page. Okay, all right, so now we are ready to start working this particular problem. And so what we're going to do is so the first problem is we want to find the magnitude of the centripetal force acting in the car when it rounds the curve. So if anything asks you for the magnitude of the centripetal force, they're asking for the essentially the net force, so the sum of forces or the net force that is directed inwards, okay? Which means we're going to do it in the radial direction, right? And we just basically want to find out what the left-hand side of that equation equals to. So the left hand of that side is the sum of the forces in the radial direction equals mass times acceleration in the radial direction. Now, in this case, there's only one force in the radial direction, so the sum of forces in the radial direction is the same as the magnitude of that single force, or the magnitude of the sum of forces is the same as the magnitude of that single force. So I'm just going to replace the sum of the forces in the radial direction with the only force that exists in that direction, which is friction. And I'm going to note that it has a negative sign because it's in the opposite direction of R. Okay, so I'm going to do equals, and let's see, mass. And for the radial acceleration, we're always going to do negative a sub c, right? So we're always accelerating inwards. at, the magnitude a sub c, right? And the reason, of course, that I leave it as a sub c and I don't write it as just v squared on r is because sometimes it's not v squared on r. Sometimes we want r omega squared. It just kind of depends. And sometimes in some of these problems, the way they're set up, we may actually have already calculated a sub c, and so we may want to leave it as such. Okay, so at this point, let's see, we're just gonna start expanding. So the force of friction equals the mass times negative. In this case, they gave us the velocity and they gave us radius. So I'm gonna use v squared on r here. And we're gonna rearrange and we're gonna solve this sucker. Okay, and I'm gonna box that because that's the answer right there, essentially. I will note that we're gonna use this particular equation again. So I'm going to go ahead and number this as number 1, just because I know. All right, so let's go ahead and plug in some numbers. And we'll note that the force of friction is 2,000 newtons, expressed in this way in order to, account for the sig figs. So, 2.00 kilonewtons. All right, so cool. So then in part B, on the other hand, we want to know, well, what happens if we triple the velocity, right? What happens to that centripetal force? So essentially, how much force is required to make this car turn if we're going 3 times as fast? And so if we look at that equation 1, where we've got the force of friction equals the mass times the velocity squared over r, we'll notice that the force of friction required is going as the velocity squared. So in other words, if I triple the velocity, the force of friction is going to increase by a factor of 9, okay? Which of course really, really matters, right? And so you guys have all felt this, I would assume so at some point in time. You guys are beginning to drive, and so you're learning, and every now and then you've taken a turn a little faster than you intended. And what you'll notice is that you can feel when it gets to be a little bit too unsafe, and it doesn't require very much. And the reason for that, of course, is because the force required to accelerate you inwards is going as your velocity squared. Okay, so just small increases in your velocity will have huge effects on that force and on that acceleration that you're feeling inwards. Okay, part C. What coefficient is required? What coefficient of friction is required to make the turn at 20 and at 60 meters per second? Okay, so we're gonna keep going with our kind of with our math. I will note that from above, so we're going to need to know the normal force if we're going to get to force of friction. So for part C, we're going to go ahead and do kind of a rear view of the car. Okay, and the rear view of the car, again, this is going to be a rear view free body diagram. And so, the Z direction is going upwards. And let's see, so it's rear view, which means that the R direction is outwards. So since we assumed the car was going around the turn counterclockwise, if I'm looking at it from behind, then the R is going to be going to the right, okay? And let's see, so we've got force of gravity going, force of gravity going downwards, and upwards we've got the normal force, and inwards we've got the force of friction, okay? Now what I'm concerned about here predominantly is, I'm concerned about the force of friction, right? Because I'm trying to get the coefficient of friction. But let's go ahead and see what's going on here, okay? So in the vertical, the sum of the forces in the Z direction equals the mass times acceleration in the Z direction. So the upward force is the normal force, the downward force is gravity. I'm going to leave that right-hand side alone. Okay, the next step, I'm going to start expanding. So the normal force minus force of gravity, which is mg, is going to equal 0. Okay, so this is, almost a trivial result. Normal force equals mg. Okay, it's not trivial. It's just that, it's the one that, we use all the time, right? It just shows up all the time in flat situations. Okay, now cool. So I want to now take that first equation that I had from this thing, that I got from the overhead view, and I want to go ahead and I want to combine these two results. So basically what I want to do is I want to say force of friction equals mv squared on r. That's the result I got earlier. And I want to expand that, right? So the force of friction is mu times the normal force equals mv squared on r. And then I want to expand again because the normal force now is mu mg equals mv squared on r. Okay, so let's see, we're going to do a little algebra, and we're going to get that mu, which is what we're looking for, is v squared on gr. Okay, and of course that's obviously the minimum you need, otherwise you will slide off the road. Okay, so we're going to need to do a little algebra on that, you know, for the two cases, the 20 and the 60. And what you're going to see is that, you know, with sig figs, the mu 20 is 0.408, and the mu 60 is 3.67, achi-machi, which basically means that it is not possible. You cannot make this turn at that speed with that radius if you're relying on friction alone. Okay, I don't know, you know, I didn't really pick the last problem to prove that you could do it if you bank the turn, which I guess would have been more interesting. I should have looked into that, but I did not do it that way. Okay, so anyway, now we're on to part D, where we ask, you know, what would be the maximum safe speed to make the turn if the coefficient of static friction was 0.61. So all of the relevant physics that we did for part C still hold. So that equation that we just derived, mu equals v squared on gr, still holds. Okay, but this time, instead of solving for mu, we're given mu, and we want to know v. So I just got to rearrange that equation, right? So if I rearrange that equation, I'm going to get v equals mu gr square rooted. Okay, so that's just a rewriting of the old thing. Okay, so if I'm going to plug numbers in, you know, so if I just plug in those numbers of 0.61, 9.81 meters per second squared, and a radius of 100, I end up with a velocity of, you know, with two sig figs of 24 meters per second. Okay, which seems reasonable, right? So, you know, the coefficient of friction is larger than it was, you know, than that necessary to make the turn at 20. So we should be going a little bit faster, and we were, in fact, able to go a little bit faster. So that, you know, that passes the pig's test. All right, so now we're going to get into the most interesting parts, okay? So if you were able to follow along with that, we're now going to get over into part E. Okay, how much would the road need to be banked if there were no friction and V is 20 meters per second? And then honors, what would be the minimum coefficient of friction if the turn were banked by 15 degrees for the 20 meters per second speed? Okay, so these both involve a banked road. So for a banked road, we're going to need a free body diagram from the rear of the car. And what I want to do is, yes, I want to imagine from the behind of the car, just kind of like I did a second ago. But this free body diagram is going to have a car on a banked road. So my car is a dot, and I'm going to do kind of a dashed line, and I'm going to do it really light because I'm going to erase it later. And the reason for that is because you know that I don't like you to draw anything other than the three things that are designed that go onto this free body diagram, right? And so so here's my car. It's on a banked road, and we need to get our coordinate system. Okay, so Z direction is straight up. Remember, this is the rear of the car, so the car is going into the page, or it's going into the page, right? And so because it's going into the page, that means the radial direction is to the right, okay? And the tangential direction is straight ahead, okay? So let's see. So now let's think about the forces on this car, okay? So if that is the road that we're looking at, let's see, we've got a normal, well, you know, anytime we've got a surface, we've got a normal force going perpendicular to it. Okay, we've got a force going along the road, that's the frictional force. Okay, those two are always perpendicular to each other. And then I've got gravity going straight down. Okay, and now to help me kind of to get at the geometry that I'm about to be playing with, I'm going to add a dotted line in the negative r direction. And I'm going to label theta. Okay, theta in this particular problem is 10 degrees. Okay, now because I find it distracting, I'm going to erase the road. I don't particularly want that road becoming a hindrance to me seeing what it is I'm supposed to do. Okay, so this is my free body diagram. So this is a car making a left-hand turn. Okay, with a banked road. All right, so now we're gonna do this math. Now I want to note that for part E there is no friction because this is the no friction example. However, I'm just going to leave it on my free body diagram because it'll help with part F. Okay, so let's see what we've got here. Excuse me. Get some water. Okay. Now, if it's like most problems that we did in the past, usually you want to do the up-down direction before you do the left-right. It's not necessarily going to be that clear to you, I wouldn't think, which way is going to be the correct or the easier way to go. But if you remember from chapter 4, a lot of times it's easier to do the up-down first so you can get the normal force, right? So let's see if that works here, okay? And it may not, and if it doesn't, then we'll adjust, right? So in the vertical direction, I've got the normal force, okay? And I want to note that it's not going straight up, it's going off at an angle. So that is going to be the cosine of theta, okay? And then in the downward direction, I've got the force of gravity. Okay, and remember, we're ignoring that force of friction, equals mass times acceleration in the z direction. Okay, cool. So now we're going to start to expand where we can. So the normal force cosine of theta minus mg equals, now on the right-hand side, that becomes a 0. So we'll rearrange this, and we'll get our normal force is mg divided by the cosine of theta. Okay, and those are all knowns. So if I wanted to, I could calculate a number right now, but I don't think that that's necessarily a good idea. Okay, so let's go to the sum of the forces in the left-right dimension, which is r, equals mass times acceleration in the r direction. We will note that the normal force is in the negative r direction, right? And of course, the gravity is not playing a role in the r direction. So this is kind of nice, right? So in the r direction, we've got negative normal force. And we note that in this case, the r component of that force is a sine. Okay, it's the opposite side for that particular triangle. And then, so that's the only force in the r direction. And so then we'll do mass times acceleration centripetal, right? And of course that has a negative sign. Okay, so cool. So we look like we're getting ready to go. We want to expand things. So in place of the normal force, I'm going to put mg cosine theta with and then I'll multiply that times sine theta equals m, and then I've got negative ac. Okay, so for this particular problem, we've got v squared on r. We don't want r omega squared here because we don't know omega. Okay, so at this point, we're going to do a bunch of, we do some algebra, so those negative signs are going to go away, the m's are going to cancel. Sine over cosine, from math class, is a tangent, so I'm going to get g tan theta equals v squared on r. And now it's just a case of remembering what I'm solving for here, which it turns out is theta. So theta equals v squared on r, inverse tangent. Okay? So that's how we solve it. We'll plug in numbers, and we will get an angle of theta is 2,3 sig figs. It's going to be 22.2 degrees. Okay, pretty fancy, right? Pretty cool. All right. Now we're going to do the part F, which I consider an honors caliber problem. It's not that the regulars can't do it. It's just that you're going to get bogged down in the algebra here. Everybody's going to get bogged down in the algebra here. I get bogged down in the algebra here. So it's really more of a time issue than anything. But let's go ahead and do this, and we're going to refer to figure E, and we will include the force of friction. So what we're going to do here is we want to know the minimum coefficient of friction if the turn were banked by 15 degrees. Okay, so let's go ahead and let's go ahead and solve this. Okay, so it's kind of just a different set of givens. Okay, and so I'm going to do the sum of the forces. I'm going to try to follow the method that I just did a second ago, and hopefully it works. And we shall see, right? So in the vertical direction, if I sum forces, it looks just like what I did a second ago, except I've got an extra force, right? So I've got, I've got normal force cosine theta. I've got minus force of gravity, but I've got an additional minus the force of friction. Now we must note that the force of friction in this particular case, the z component of that is going to be sine of theta, right? It's a sine because it's the opposite of that angle, equals MAZ. Okay? Now we're going to go ahead and we're going to start expanding where we can. So normal force cosine theta. I can't do anything with normal force because I don't know it, right? The force of gravity is mg. And the force of friction, well, why don't we get that into terms of normal force, right? Mu Fn sine theta, okay? And the nice thing about this particular equation is all of this adds up to 0 because we are not accelerating up or down. Cool. So if I rearrange this and I solve for the normal force, well, I'll show one intermediate algebraic step, but ultimately we're going to end up with the normal force is mg over cosine theta minus mu sine theta. So what really stinks here is that normal force is an unknown, and I'm pretty sure I'm going to need it to go into the other equation, and so that's why I solved for it. But the problem is part of what it is has mu in it, the thing that I'm looking for. So that's going to make the algebra get a little bit gross. Okay, and whatever. We'll deal with that when we get there. It's not like we can't do algebra. All right, so then on the right-hand side, not the right-hand side, on the left-right acceleration equation, Newton's second law, sum of the forces in radial direction equals MAR. Again, it's going to look just like it did for the problem beforehand. So I'm just going to go ahead and copy that equation down. And however, we've got an additional force, right? We've got the force of friction. So in this case, I'm going to subtract force of friction times the cosine of theta. Now we know that it is negative because the force of friction is causing it to go in the negative r direction. Okay, so cool, we've got all this stuff. Let's go ahead and let's try to get this in terms of the normal force because that's what I solved for on the right. Okay, Fn sine theta minus force of friction, which is going to be mu times the normal force, cosine theta, equals, and then on the right, of course, we know, because we've seen this now enough times, I hope, that this is going to be v squared on r. Okay, the first thing I'm going to do here, because it just, all those negative signs annoy me, so I'm just going to turn them into positive signs. It's going to make my life a little bit easier. And then, let's see, and then I'm going to try to pull out that normal force. Okay, so I've got normal force. Let's see here, sine theta plus mu cosine theta equals mv squared on r. Okay, cool. So now the beauty of this now is I've got two equations and two unknowns. I've got mu and normal force. So I need to plug them into each other. And so I think I'm going to put the normal force in now. I'm going to plug in for normal force. So we'll get mg cosine theta minus mu sine theta times sine theta plus mu cosine theta equals mv squared on r. Now, why did I do that? The whole point, of course, was I don't really care what the normal force is. I'm not solving for that. So that's why I plug in for it. So now it's gone. So now I just have an equation with mu as my only unknown. So we'll note that both sides have an m multiplied by both sides. So the m's are going to go away. And then the rest of this algebra, I'm going to put on the screen. But I think you can just download the solution and follow along there if you really want to spend more time on this. But I guess, anyway, ultimately what you end up with is you end up with the expression that mu equals v squared cosine theta minus gr sine theta divided by gr cosine theta plus v squared sine theta. Okay, a big nasty expression, and if you plug and chug into that, you'll get that mu with 2 sig figs is 0.13, which I think is really, really impressive when you think about it. that the coefficient of friction would drop this much with a banking of, so little, right? So, a couple of steps ago, we found that to go 20 meters per second, you would need a mu of 0.408, right, in order to make that turn. Well, if you bank that turn by 15 degrees, your required mu drops to 0.13, right? So that's really, really, really impressive. And of course, the reason for that is now you've got the normal force helping you out and not just the frictional force, right? And the frictional force actually becomes less effective because it's no longer directed straight inwards. However, always remember that the frictional force is only a fraction of the normal force, right? So the normal force is not being reduced by a coefficient of friction. So any amount of help that you can get from the normal force is going to decrease the needed frictional force by way more, right? So that's pretty cool. Okay, so anyway, that's all I got for now. So this is about 25 minutes. So hope y'all are doing well. All right, bye.